This time we will talk about the idea of Plancherel's theorem, which is also called Parseval's identity. And we already seen in the previous times when we used the Cauchy-Schwarz inequality that we were able to connect the the angle between two functions, which is the inner product, into a product of, let's say, L2 norms of the two functions we have there. But then in order to go into the Fourier analysis side, in order to apply the Fourier analysis in this, after we apply the Cauchy-Schwarz, for example, is this very powerful theorem called Plancherel's theorem, which is a kind of preservation of the L2 norm up to a constant that depends on the group, ZP, for the Fourier transform of its L2 norm. So in some sense, it allows you to conserve the Fourier transform. So you can connect if you are able to bound, let's say, the L2 norms of the Fourier transform instead of the original function, you might actually it might be easier in the Fourier side. And that typically is the case, that once you have taken a very, let's say, a complicated function f that might represent some kind of a geometric problem or probabilistic problem like we are considering. We will later see that there will be the functions we are applying this Plancherel's theorem will be on certain functions that depend on the probability or the geometry of the space. And then in the Fourier side, we have something far simpler that only depends on the Fourier transform. We can maybe use some methods of complex numbers, for example, to be able to estimate those things much more easily. It's not always the truth, so this is not like a magic trick that will solve everything, but it does turn out to be, like in many applications, quite a powerful method. So let me go into the basic things of what it is. So this week let's say start week 7, we start with this idea. So the first topic is the Plancherel's theorem, also called Parseval's identity. I have seen a few names for it. And there is also some people call it the L2 isometry theorem for Fourier transform, for example. So what the basic statement of theorem is, so it's a theorem that says the following, that if we have two functions, f and g, which are functions from ZP to the complex plane, then basically the inner products or the angles are preserved up to a constant that depends on the groups, which is just 1 over p, the cardinality of the group, and then you have the Fourier transforms of these two functions. Okay, that's all it's saying. So in particular, this is the connection to the L2 norms, that if f is equal to g, we have that the L2 norm, of course, that if you take the L2 norm, remember that this L2 norm was just the square root of f. So then this just becomes, if you use that identity, 1 over the square root of p, and then you have the Fourier transform of ff with itself. So this becomes an f, well, I could put this f Fourier transform square root of this, and then this becomes 1 over square root of p, and we have the L2 norm of the square Fourier transform. Ooh, there's a bit 2 here. Yeah. So this is the Plancherel's theorem. So let's look at this a little bit. So what it's saying basically is that if you think about this function, so remember that you have this function f from ZP to C, and if you have a g function from ZP to C, you can think about them as vectors. So you can identify as vectors in CP. So you can think about that f is a vector in CP, because you can think about the f in some sense being this element, and you have the value at 0, value at 1, and then value at p minus 1, which is an element in CP. So it's an identification. And the reason I want to do this is because now you can think about this as a vector space. So complex plane to the power p, that's a vector space. So it has Rn or something like this, just complex numbers in the plane. So now if you think about the inner product, for example, f inner product G. And this is really an inner product that you would see of the vectors. So this becomes really this summation if you open this up, ft and gt bar t in zp. And what is this saying basically? That then as vectors, if you compute the Fourier transforms of these things, so this is the Plancherel, you get that this is 1 over p, and then maybe you sum of k in zp of the Fourier transforms as vectors, g, k, Fourier transform and the complex conjugate. So, which is the 1 over p f bar g bar. So in some sense, if you think about this as vectors, like you could think about now the Fourier transform as well, vectors in also as a vector in zp, so like f bar would be then, think about f bar 0 and f bar p minus 1 in c to the power p, then you have this kind of idea that if as vectors, so if you think about like in some sense this would be a vector the f, and this would be the vector g, this would be in the vector space c to the power p, then in some sense this angle is almost preserved in the sense that it just depends on the group. So if you have the Fourier transform here, you get the same angle, but you have to multiply it by this constant. So in some sense maybe I could take this down and maybe move it slightly, so this depends on here. So if this is like the angle, then in some sense you could say that this is 1 over p alpha. So it's only as a constant multiple of this, these two angles that depend on this, what happens to the Fourier transform. So that's kind of what is the Plancherel's theorem saying you. You can control, if you understand how orthogonal your functions are, like are they orthogonal, for example, then they are orthogonal. So in particular, for example, if you have an orthogonal angle here, like this is a right angle for two functions, f and g, then this implies that also these have to be, well, in some sense this is not multiplication, the angle depends on, of course, the inner product. So there's a formula for it using the cosine of that. So this is not exactly true. You could maybe write this as a as a cosine of this. So this is not exactly. I would maybe write this as a some function that depends on alpha. Maybe I would maybe use a cosine of alpha or something like this. I think that's how you would maybe use it. If this is cosine of alpha, the angle that you use, then I think it's something like that. How to connect this, but the same idea goes here. That actually these are orthogonal as well in here. So you have this that if the inner product of f and g now is 0, then also the these Fourier transforms have the same inner product, which is equal to 0. So the orthogonality of these functions is preserved into the Fourier side as well. So that's kind of the basic idea of the Plancherel's theorem. And the usefulness of this comes like in many applications, which we will see later on when we use the probabilistic method. But let's prove this now. So that's the last thing I wanted to say today about the proof. So what we start here is we start from the two functions f and g, and we actually start from this side. So we use the definition of the inner product. Maybe use actually k here. So f bar k, g bar k for a transform like this. And now we just basically, okay, let's go a bit backwards here. So let's all give some space. So we have still the k in zp, a sum here, but let's open the definitions of the Fourier transform. So we have the t in zp, and we have ft e to the power minus 2 pi I k t over p. So that's the definition of the Fourier transform of f. And then we have the complex conjugate of what? So we have the Fourier transform of t, g. So gt, maybe I'll actually use a different letter here because it's actually a different sum. So I'll use s here instead. So minus 2 pi I k s over p. So you can see that there's an s here, and then there's a t here that you're taking the summation over. Put this here. And then there's a third quantity, which is the k. So just to show where the k dependence is on all of these quantities. Okay, and now you can use the complex conjugation, that when you have a sum of numbers and take the complex conjugation of the sum, it actually goes inside because of the linearity of the complex conjugation. So what you can do here is that I actually open up these expressions. I sum over zp, I take the ft here, e to the power minus 2 pi I k t over p, and then I have the sum here of s in zp, and I can put actually the complex conjugation inside here. So I can put here complex conjugate, and then the complex conjugation of the minus 2 pi I k s over p, complex conjugation of this one, but then this one over here is equal to just 2 plus with that I k s over p. So this way we have an expression now that we have like everything in one sum, so we have the complex conjugation everything here. So what we can do now is to rearrange the sum. So what my aim is somehow in the end to get something like this, that maybe if I want the main theorem to hold, what I want is that there would be like a p times fg. So this is what my aim is to get. So in some sense I need to find the inner product of f and g out of here and then multiply a constant that maybe come out from the complex expressions that I have here. So in order to do that, let's try to rearrange the sum to be getting into that kind of a form. So what we can do is that, okay, we take this sum here and we actually rearrange this. So we have the sum over t here, as you can see here. So let's take that first. So that's like t in zp ft. So that's what I would have in the product. But then I have a problem here that then there's a sum over s in zp, and then the complex conjugate of g here. And in some sense I would need to arrange this into is this equal to, let's say, t, just equal to the complex conjugate of t. I don't know. This is like what I would like to get, but I'm not sure if this happens. But actually it does happen because of the complex numbers we have here, because we have still the multiplication over, then we have the sum of k in zp, so this sum is rearranged inside. And what is left here is this term here that depends on k, and then this term here. So if you take their product, it's e to the power this, and it becomes a multiplication. You can actually write this as minus 2 pi I as before, and you have the k. And now you can see that there's a t here with negative, and this is positive. So what we have here, if we have a negative here, we can put t minus s here and then divide by p. So that's the expression you obtain. And now the final thing here is that if you look into this expression, what we have here, we can actually write this as this becomes p if t is equal to s, and this is 0 when t is not equal to s. This is basically, the reason for this is the complex summation formula. So if you look at the expression what we have here, maybe I could write this here, y, is that writing this like, I would write this as theta, which is equal to minus 2 pi I, I think I would use maybe t minus s over p actually. So if t is equal to s, then this implies that theta is 0. So we are, so this expression here, so this, if you take this e to the power I theta, I k theta, k from 0 to p minus 1, that's the summation we are considering here. This sum over here is actually this same summation. This summation is just summing ones, because now it's just p minus 1, 1, so this is just equal to p. And if we have that t is not equal to s, then that implies theta is not equal to 0. So by geometric sum formula for complex exponents, this is what we have stated already in the previously in the course. We have the k minus 1 e to the power I k theta. You can write this as 1 minus e to the power theta power I, and then e to the power theta I. But because this is an integer, so because the as t minus s is an integer, this implies that e to the power p theta I, which is equal to e to the power minus 2 pi I t minus s over. It's just t minus x because you're multiplying the p out in the front in the definition of theta. Theta depends on p, you're dividing by that quantity. This is just equal to 1, so this is because it's an integer, because this is, if this is an integer, then you get integer multiple of pi, you get 1. So that implies that this is this k from sum to p minus 1 I k theta is equal to 0, because then this is equal to 0. So that's why we have this proof for this. So this is equal to p at these points, t is equal to s, and then 0 at the other points. So that means that inside this summation you can see that once you fixed your t over here, then there's only one expression where this is non-zero, and that's when t is equal to s. So when s is equal to this t that you have fixed here, you can actually get something non-trivial. So if you continue this, so let's continue this expression, what we have here after this. So this is like maybe I'll use an arrow here, so it's a bit messy, but going down into here. What we obtain is that this is the sum over t in zp of ft, and then you have the only one expression, which is a g of t bar, and then you have p here. That was the only thing that remained from the expression of the sum for the last term, that this is equal to p at those points, and then this summation has only one element because all the other terms have 0. So this is just precisely, once you take the p out, this is equal to f and g. The inner product. So this proves the Plancherels theorem. Okay, so that's kind of the main kind of idea what you have about the Plancherels theorem, and it's a useful like exercise kind of thing, which I could maybe talk about a little bit more. But we will see later on that this is gonna be quite useful in the exercises and in the proofs of the theorems, in the main theorems of the course, when we use this theorem in this way. The proof is quite simple, but actually, if we would do more general groups, this proof would complicate a little bit, because there would be difficulties to actually understanding what is actually the Fourier transform, for example. What would it mean to, what does this mean, for example, in a more general group? What is the Fourier transform? So that you have to actually open up the definition a bit more and try to understand that. But we'll come back to this a bit more later. So that's all for today. Thanks.